Hello students, back to part 3 of section 11.10. Today we will discuss the Maclaurin series for 6 famous functions, which are ex, sine x, cosine x, tan inverse, the ln, and 1 over 1 minus x. Now, in each one of these, we can do exactly what we did before, making a table. Okay, and then we find the derivative. And then we substitute the derivative at 0, and you are wondering why 0, because it is Maclaurin series, so we substitute at 0, and then we find Cn, which is the derivative at 0 over n factorial, and that will be the coefficient in the power series. Now, luckily for those 6 functions, the formula, we can do this table and we can find the formula, but what we really need now is not finding the formula. You can read it in the book, but we need to write them down because we will use them heavily in the coming few lessons. So we start with 1 over 1 minus x. I think this is familiar. We already did it. This is the geometric series. And as expanded form, it's 1 plus x squared plus x cubed. And as a closed form or sigma notation, this is from 0 to infinity, x to the n. Of course, the radius of convergence is from -1 to 1. This is the interval, and the radius is 1. Keep in mind, this is converges only if x between -1 and 1. So this is number 1. Number 2, of course, tan inverse and ln x, we already did them. I will not write them down here. We can go back and see them. Ex. And here I want you to memorize it with me. It will be exactly the same as this one, except we have something in the denominator. So it will not be x to the n only. It will be x to the n over n factorial. That's the ex. So almost, if you know what is 1 over 1 minus x, a quick twist, you can find e to the power of x, and as I said, it's exactly the same, except x over n factorial. So it will be 1 plus x squared over 2 factorial plus x3 over 3 factorial, x4 over 4 factorial, and so on. Here, it is also over 1 factorial, but 1 factorial is already equal to 1. Here, 0 factorial and 0 factorial already equal to 1, so we don't need to write them down. But they are there, but we don't need to write them down. 3 is sine and cosine, and let me use the white color here. Now, sine and cosine, again, if you want a quick way to remember them, they will take everything from ex. But sine will take the odd power, cosine will just take the even power. So sine will take only the odd power. So it will take x cubed over 3 factorial, x5 over 5 factorial, and so on. That's the sine. So it will be x cubed over 3 factorial, x5 over 5 factorial, and so on. Now, there is a twist in the sign. It is alternating. So it is almost the same as ex, but it will be alternating. So this would be negative, this would be plus, the next one would be negative. So if we try to write it as a closed form, remember we are taking the odd power, so it will be 2n plus 1. And the factorial is exactly the same as the number in the power, so it will be over 2n plus 1 factorial, and then it's alternating, so it's -1 to the n. That's the sign. Now for the cosine, we said we take the even power, and again it will be alternating, by the way. So it is minus, and then x4 4 factorial, and then x6 6 factorial, and so on. Which is, if we write it as sigma notation, this is the even powers over even factorials, and it's alternating, so it is -1 to the n. Now, please find a way to memorize all those 4 formulas. They are very much important for us. They are very, very important for us. The tan, I can't even write the tan. Let me do it in a different color. The tan inverse of x. It's exactly like the sine, but without the factorial. So it would be x minus x cubed over 3 plus x5 over 5. And I guess this one will be x7 over 7 and so on. Which is just take the alternating, take the odd power, and off we go. Now for the radius of convergence, all of these are from negative infinity to infinity. So they are converges everywhere. We don't need to care too much about them. Except I think number 6, which is the len. And the len will be just integration of this one, but with alternating. So it will be x squared over 2, and so on. So number 6, go back and see them. 1 plus x. They are x minus x squared over 2 plus x3 over 3 minus x4 over 4, and so on. Which is alternating. So this is negative 1 to the n. And then x to the n over n. And here n start from 1 to infinity. Just I write n plus 1 to fix that the first term should be positive. Yeah. So please keep this in mind. We will need them whenever we use them. And let's go and see how we will use them in several examples. Oh, the first one, he wants me to find arctan of x squared. That's easy because what is arctan? Arctan is the same as tan inverse, by the way. So it is tan inverse. Now for tan inverse, I know exactly what is the formula. Remember, the formula for tan inverse, it is exactly, if I just write it as expanded form, start with something and then alternating. So something and then something power 3 over 3 plus something power 5 over 5 minus something power 7 over 7. Of course, start something. And so on. Which if you do it as expanded form, it is alternating and then something to the odd power over the odd power. Now, what is the something? It's only the input. If it's x, I write x, 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 x. Now we have x squared, so this is x squared, and x squared. So just let me write x squared, x squared, x squared, x squared, and x squared. Now this one you can expand it very easily and you get the final answer, which is x squared minus x6 over 3 plus x10 over 5 minus x14 over 7, and so on. And if you do it as sigma notation, it will be alternating, and then it will be 4n plus 2 over 2n plus 1. And that's exactly what you need to write for the Maclaurin series. Now remember, this one you can do it with the table, but it will be lots of work because you need to see the pattern. Now this method is much easier because if you know the tan inverse, just replace x with x squared, you get what you need. Doing with the table, finding derivatives, it will take a lot of time, a lot of work, and finding the pattern might not be as clear as it looks. Just to warn you here. Next example, we have x and then we have cosine of something. So I guess we do the same thing as before. So f of x, x cosine of x squared over 2. Now for x, we'll wait. Now for the cosine, we have to write the I will do the expansion form now. What is the cosine? Cosine was 1 minus something square over 2 factorial plus something power 4. Remember, it was the even powers. And that's it. Now in each one of these, we don't write x, we write x squared over 2, x squared over 2, x squared over 2, x squared over 2. Now we do a little bit of expansion here. So we get 1 minus, this will be x power 4 at the top over 2 squared times 2 factorial plus x power 8 over 2 4 times 4 factorial minus x 12 over 2 6 times 6 factorial plus x 16 over 2 8 factorial. And the last step gonna be take the x inside. So the final step will be x minus x 5 over 2 factorial plus x 9 over 2 4 factorial minus x 13 over 2 6 factorial plus x 17 over 2 8 factorial, and so on. And that's the expanded form. If you want, you can do the sigma notation form, and that I will leave it for you as an exercise to practice. It's very important to practice those questions. I assure you that those are very important for the coming lessons, not just for this question in particular, but when we do integration, derivative, finding limits, approximation, we will need to deal with cosine, sine, ex easily by changing the input. Oh, sine square of x. Now, this is a tricky one because if it's only sine, we know how to deal with it. Now, the problem is here we have sine square. So, we can have 3 options here. Let me write them down for you, just not to forget them. Option 1, to use the table. Not recommended. As usual, I don't recommend we think of the table. Table means finding derivative, after derivative, after derivative, and then finding a pattern. Maybe you are not good at finding the pattern. Maybe the pattern is so complicated you cannot really find it by having seen few terms. So I'm not recommending using the table. Second one is you find sine x and then you multiply it twice, which means you find the series for sine and you multiply it by the same series of sine, which again, because those are infinite series, the final answer will be difficult to spot a pattern. That would be difficult to spot a pattern. Not recommended. Option 3, think of another way, which is the same way we did it when we do integration of sine square of x. Do you remember when we do integration for sine square of x? We use a formula. Pause the video and remember the formula. Exactly, the formula is double angle formula. And what's the double angle formula? Here we go. Sine square of x. Double angle formula, it is 1 over 2, 1 minus cosine 2x. And from here, everything is easy because this is half, this is 1, this is minus. And here, you write the Maclaurin series of the cosine. but you replace every x by 2x. So I will leave it for you to practice it by yourself to finish it up. Thank you very much for watching this part, and if you have any question, please write it down for me in the comments.